Hello everyone, let's look over chapter 12, liquid, solid and intermolecular forces. Let's check properties of the liquid and solid. In contrast to gases, in which molecules or atoms are separated by right distances, molecules or atoms compose a liquid and solid are close contact with one another. The difference between solid and liquid is in the freedom of the movement of the constant molecules or the atoms. When you see liquid, even though atom or molecules are in close contact, they're still free to move around each other. In solid, atoms or molecules are fixed in their positions, although thermal energy causes them to vibrate about a fixed point. So gases, low density, indefinite shape. They assume the shape of their container and indefinite volume. They are easily compressed. For example, carbon dioxide gas. When you check the liquid, high density in comparison to gases, so indefinite shape, they assume the shape of their container. The definite volume, they are not easily compressed. For example, liquid water. When you focus on the solid, high density in comparison to gases, definite shape, they do not assume the shape of their container. Definite volume, they are not easily compressed. For example, the sugar. Okay, let's know definition of intermolecular forces. Intermolecular forces are attractive force between molecules. So most important manifestations of the intermolecular forces is the very intensities of a liquid and solid. Without intermolecular forces, solid and liquid would not exist. All matter would be gases. In liquid, we can observe several other manifestations of the intermolecular force, including surface tension and viscosity. We need to know definition of the surface tension. Surface tension is tendency of the liquid to minimize their surface area. For example, the paper clip will float on the water if it is carefully pressed on the surface on the water. It is held up by surface tension. You cannot float paper clip on gasoline because intermolecular forces among the molecules composing gasoline are weaker than intermolecular forces among the water molecules. Definition of viscosity. Viscosity is the resistance of the liquid flow. The maple syrup is more viscous than water. So, stronger intermolecular force equals more viscous. Weaker intermolecular force equals less viscous. It means maple syrup has a stronger intermolecular forces than uh, water. Vaporization, condensation, thermal energy. So evaporization, because molecules on the surface of the liquid are held less tightly than those in the interior. The most energetic among them can break away into gas state in the process called evaporation. The rate of the evaporation increases with increasing surface area, increasing temperature, decreasing strength of intermolecular process. Condensation is a physical change in which substance is converted from its gaseous state to its liquid state. That's condensation. So evaporation and condensation are opposite. So evaporation is liquid turning into a gas. Condensation is a gas turning into a liquid. At the point with the rate of condensation, evaporation become equals. It's called a dynamic equilibrium. We can interpret a heating curve during boiling. The mixture of the boiling water and steam will always have a temperature of 100 degrees Celsius. When you see at 100 degrees Celsius, you can see here liquid and gas of the water. Only after all the water have been converted to steam can temperature of the steam rise beyond 100 degrees Celsius. Over 100 degrees Celsius, you can see rise temperature. So only you can see here that only gas. Amount of heat required to vaporize 1 mole of liquid is the heat of vaporization, delta H VAP. Heat of vaporization of the water at its normal boiling point 100 degrees Celsius is 40.7 kilojoule per mole. Heat of vaporization is positive because vaporization is endothermic. So energy must be added to water to vaporize it. So liquid to gas, the endothermic reaction. So it means delta H is positive. So condensation is exothermic. Energy is given off as water condensates. So for example, gas to liquid. That's exothermic. So that it means delta H is negative. Okay, let's solve problems. Calculate amount of the water in grams. Can be vaporized at its boiling point with 155 kilojoule per of heat. First, you have to convert kilojoule to more water. Second step, convert more water to gram water. So for step 1, you need to use heat of the vaporization. I provide a heat of the vaporization of the water. You don't need to memorize. Okay, but use heat of the vaporization, convert kilojoule to more water. And then step 2, you have to convert more water to mass water, gram water. So use molar mass. So right now, given number unit on the left side, we need two conversion factor. So from heat of vaporization and molar mass. So finally, we can get 68.6 grams. Okay, let's interpret heating during the melting. A mixture of the water and ice will always have a temperature of the 0 degrees Celsius. At 0 degrees Celsius, you can see here solid and liquid mixture. Only after all of the ice has melted with additional heating, rise the temperature of the liquid water past 0 degrees Celsius. Past 0 degrees Celsius, you can see only liquid. Okay? Between 0 degrees Celsius to 100 degrees Celsius, you can see only liquid of the water. And below 0 degrees Celsius, you can see only solid. The next, amount of heat required to melt 1 mole of solid is heat of the fusions. Heat of fusion of the water is 6.02 kilojoule per mole. So melting is endothermic because energy is required to partially overcome attraction between molecules in solid and free them into the liquid state. So solid to liquid, that's melting. So that's endothermic. It means delta H is positive. Freezing is an exothermic, liquid to solid. Heat is released when liquid freezing to a solid. So it means delta H is negative. Okay, let's solve problem. Calculate amount of ice in grams. Upon melting, observe 237 kilojoules of heat. So first convert kilojoule to mole and mole to mass. So first we need heat of the fusion. You don't need to memorize. I provide the numbers. Okay, you need molar mass. So right now, given number unit 237 kilojoule time, we need two conversion factors. First one, I provide heat of fusion of water, and then you need to use periodic table to get molar mass of the water. Finally, you can get 709 grams of water. Okay, let's understand diagrams. Diagrams show the heating curve for ice beginning at minus 25 degrees Celsius, minus 25 degrees Celsius, ending at 125 degrees, 125 degrees Celsius. Correlate section 1, 2, 3 with correct state of the water. Okay, Roman numeral 1, 2, 3. At 0 degrees Celsius, we can see solid and liquid. And Roman numeral number 2, between 0 and 100 degrees Celsius, that's liquid. At 100 degrees Celsius, you can see liquid and gas. What about beyond the 100 degrees Celsius? You can see only gas. Below 0 degrees Celsius, you can see only solid. It is good to know, memorize names of processes. Sublimation is a physical change. Substance change from its solid state direct to its gaseous state. That's sublimation. Solid to gas, that's sublimation. For example, dry ice is a solid carbon dioxide under atmospheric pressure. At minus 78 degrees Celsius, carbon dioxide molecules have enough energy to leave surface of the dry ice and become gases. Can you see? Solid to gases. So memorize names of process. Solid to liquid, that's melting. Liquid to solid, that's freezing. Liquid to gas, evaporation. Gas to liquid, condensation. Gas to solid, gas to solid, that's deposition. Solid to gas, that's sublimation. Okay. Type of intermolecular forces. Number one, dispersion. Number two, dipole-dipole. Number three, hydrogen bonding. So intermolecular forces are attractive forces between molecules. But intramolecular forces hold atoms together in molecules. So 41 kilojoule to vaporize 1 mole of water, that's intermolecular forces. 930 kilojoule to break all OH bond in 1 mole of water, that's intramolecular forces. So generally, intermolecular forces are much weaker than intramolecular forces. You can measure intermolecular forces by using boiling point, melting point, enthalpy of vaporization, enthalpy of fusion, enthalpy of sublimation. Okay, let's focus on dispersion forces first. Dispersion first, default intermolecular forces present in all molecules and atoms. Dispersion forces are caused by fluctuations in the electron distribution within molecules or atoms. Since all atoms and molecules have electrons, they all have dispersion forces. Electron in an atom or molecule may, at any one instance, be unevenly distributed. So an instantaneous dipole on any one helium atom induce instantaneous dipole on neighboring atom. The small circle is nucleus. There are two electrons. Okay, that's helium. Between helium molecule, you can see delta positive here, delta negative. That's dispersion force. And second, dipole-dipole forces. Dipole-dipole force exists in all polar molecules. So polar molecules have a permanent dipoles. Interact with permanent dipole of neighboring molecules. For example, formaldehyde CH2O, that's formaldehyde. Structure formula of formaldehyde, this one. It's a polar. Therefore, have permanent dipole. So electronegative value of oxygen 3.5. Electronegative value of carbon, that's 2.5. So you can put delta minus on oxygen, delta positive on carbon. So positive end of polar molecule, this one, black one, okay, is attracted to the negative end of each neighbor. That's oxygen. Oxygen. So gives line to dipole-dipole force. Can you see red dot line? That's dipole-dipole forces. Effect of difference in polarity on melting and boiling point for two compounds of similar molar mass. So formaldehyde, that's polar molecule. C2H6, that's non-polar molecule. So polar molecule has strong intermolecular forces. So you can see higher boiling point than ethane, higher melting point than ethane. Okay, because formaldehyde has a strong intermolecular forces. You need to know definition of miscibility. Liquid ability to mix with another liquid without separating into two phases. In general, polar liquids are miscible with other polar liquid, but not miscible with nonpolar liquid. For example, water polar liquid is not miscible with pentane. That pentane is nonpolar liquid. For example, when you mix water and pentane, you can see two layers, not miscible. Number three, hydrogen bonding. Hydrogen bonding, you need to see hydrogen, okay? Hydrogen bond is special dipole-dipole interaction between hydrogen atom in where? NH, where? In OH, where? FH bond. And on electronegative atoms, oxygen, nitrogen, or fluorine atom. So now can you start line? There's hydrogen bond. In a hydrogen bond, you have to see hydrogen, right? Where in A and B are nitrogen, oxygen, fluorine. Okay, phone atom in here. And then next, you can see phone atoms. So can you see red dot line? You have to see hydrogen in OH bond. And next, phone atom. That's hydrogen bond. Can you see red dot line? Can you see hydrogen in NH? next phone atom. Also, you can see red dot line, hydrogen in NH bond, next phone atom. Can you see hydrogen in OH, next phone atom. Next, can you see hydrogen in NH, next phone atom. Hydrogen in FH, next phone atom. You can call hydrogen bonds. So in methanol, so oxygen 3.5, hydrogen 2.1 electronegativity values. So higher electronegativity values, so delta minus on oxygen, delta positive on hydrogen. Neighboring methanol, you can see red dot line, that's hydrogen bonding. Okay, so when you see methanol, okay, you can see hydrogen bonding. So you can see higher boiling point, higher melting point than ethane because there's no hydrogen bonding here. When you see water molecules, you can see that line. Hydrogen in OH and next oxygen, you can see hydrogen bonding. So water molecule forms strong hydrogen bonds with another. So boiling point of water 100 degrees Celsius is remarkably high for molecule with such a low molar mass. Okay, summary, type of intermolecular forces. You can see first one, dispersion force. Another name, random force. Second, dipole-dipole force. Third, hydrogen bonding. So you can see dispersion force in all atom and molecule. So relative strength, weak, but increase with increasing molar mass. For example, He2. So He2, 2.1 substrate, 0. So electronegative difference is 0. So non-polar molecule. Dipole-dipole forces, for example, HCl, electronegative value of hydrogen 2.1, chlorine 3.0, substrate 0.9 difference. Electronegativity difference is 0.9. So you can see polar covalent bond and this one polar molecule. Okay, so in polar molecule, you can see dipole-dipole forces. In hydrogen bonding, HF, you can see hydrogen in the molecule. Okay, so you can see hydrogen in FH next fluorine. So you can see hydrogen bond. So in HF, you can see dispersion first and dipole-dipole first and hydrogen bonding in HF. But in HCl, you can see dispersion first and dipole-dipole forces. Okay, but in He2, you can see only dispersion first. Okay. Okay, type of crystalline. Number one, molecular. Number two, ionic. Number three, atomic. Solid may be crystalline, well-ordered array of atoms or molecules, or amorphous, having no long-range order. Crystalline solid can be divided by into three categories. Number one, molecular. Number two, ionic. Number three, atomic solid. So for example, H2O, only non-metals, some molecular solid. Solid CO2, that's molecular solid. Carbon, non-metal, oxygen, non-metal, some molecular solid. What about table salt, NaCl? That's cation, anion, metal, non-metal, that's ionic solid. And then metal, non-metal, ionic solid. What about atomic solid? A solid whose composite unit are individual atoms. For example, silicon, gold, and xenon. Okay, a good example of atomic solid. Water has a low molar mass. Yeah, is a liquid instead of the gas at room temperature. Water relative high boiling point can be understood by examining structure of the water molecule. You can see here hydrogen bonding. Because liquid water expands when it freezes, ice is less dense than liquid water. So liquid water, that density, that's 1 gram per milliliters. But ice, less than 1 gram per milliliters. So consequently, ice cubes and icebergs float. Thank you for watching video.